Welcome back to MEC 416/816 Engineering Acoustics. In this lecture, we're going to continue in Chapter 1 and focus on what are known as damped oscillations. So we're specifically going to now look at what is known as damping. And damping adds a dissipative element to the system. And that means that there's some force acting on the system that is dissipating energy or removing energy from the system. And typically it's converting that energy into heat, although there might be some other mechanism as well. The most standard model and most common approach for modeling damping is using what is known as a viscous damper. And it's represented with the symbol that I'll highlight right now, circle right now. It's shown with that symbol, and we typically have some coefficient. In this class, we're going to use B, and it has then a restoring force of F of x dot, so it depends on the velocity, is equal to minus B times x dot, which means that it will still be a positive on the left-hand side. On the right-hand side, it's going to be negative. And I just want to note that the book uses R sub M instead of B, and they call this the mechanical resistance. In our case, we're just going to use B and go with that. So in that case, we're now going to consider the following oscillator. Let's add in that word there. We're going to consider the following oscillator. We'll draw a ground. There's our spring. Here is the damper. If you're wondering what the damping symbol represents, it actually represents a piston in a cylinder, and you can imagine that there's some type of viscous oil in that cylinder, and the piston is compressing and pushing that oil around, and that's where this viscous damping term comes from. So we'll have a spring force or spring coefficient or stiffness K, damping coefficient B, oscillator's mass M, and again, we're going to measure the motion with x of t here. In this case, the equation of motion is going to be mx double dot, that's our mass times acceleration, plus b times x dot, that's our damping term, plus k times x, and that's going to be equal to 0. And again, b times x dot, that's our viscous damping term. We're going to solve this equation of motion the same as we just did previously in section 1.1 by making an ansatz. And our ansatz is going to be the same in this case. So again, ansatz is just a German word that means educated guess. We're going to guess here that x of t is equal to some a amplitude times e to the lambda t. And we're going to then substitute that in to equation 11. That was our governing equation of motion, shown there. We substitute that in, and what we'll end up finding is that we'll get m times lambda squared plus b lambda plus k all of that then multiplied by e to the lambda t. That's all now equal to 0. And so I skipped some steps here, but it's a similar approach to what you saw in the previous section. So this equation must be satisfied for all time, which means that e to the lambda t can only be 0 provided that lambda is negative. It can only be 0 for infinite time or at very precise specific times if it's an oscillation, but it won't be true for all time. And we don't want a to be 0 because then we get no motion at all, and that's a boring solution or a trivial solution. So what that means is that the equation m lambda squared plus b lambda plus k, that must be equal to 0. And this is what you would consider to be the characteristic equation for this system. We then go ahead and divide by m, which then gives us the lambda squared plus b over m times lambda plus k over m, which we know is omega 0 squared, or the natural frequency, and that is then equal to 0. Which, this is just a quadratic equation. We can then solve this, and we'll find that lambda is equal to minus b divided by 2m plus or minus the square root of, in fact, I left out a 1/2, so let's put the 1/2 here, times the square root of b squared divided by m squared minus 4 times omega 0 squared. And again, all of that is under the square root. We're going to now make a small simplification. We're going to take the term that I'm now circling, and we're going to set that equal to beta, shown here. Beta is called the temporal absorption coefficient. And by using that, or setting b over 2m equal to that, we'll find that lambda must be equal to minus beta plus or minus the square root of beta squared minus omega 0 squared. And we've gone ahead and absorbed that 1/2 into the square root. So that's much prettier and cleaner and easier to deal with. And in most cases, what we're going to end up finding, and this is especially true in acoustics, and it's also especially true in general vibrations, we'll find that this beta term, or the temporal absorption coefficient, is going to be less than omega 0, such that the quantity inside the square root is going to be negative pretty much always. And we can then just go ahead and pull out a j, or the imaginary constant, out of that, and then rewrite that lambda must be equal to minus beta plus or minus j times the square root of omega 0 squared minus beta squared, all that in the square root, and again, j here is our imaginary constant, the square root of -1. We're going to then say that omega sub d is our damped frequency, and we're going to define it as omega sub d is equal to the square root of omega 0 squared minus beta squared, such that lambda ends up being equal to, lambda is equal to minus beta plus or minus j times omega d. So we have temporal absorption coefficient and our damped natural frequency. From there, the solution ends up being x of t is equal to e to the minus beta t times the quantity a1 times e to the j omega d t plus a2 e to the, in this case it should be minus j omega d t, which is a similar form as what we had in the previous section, except now we have this e to the minus beta t on the outside, and then also we have e to the j omega d, or the damped natural frequency, instead of this, the natural frequency. So we then use Euler's formula and the initial conditions, which we're just assuming generic initial conditions, and then we end up with the following, that x of t is equal to e to the minus beta t times the quantity x sub 0, that's our initial displacement, times the cosine of omega dt plus u0 plus beta times x sub 0. That's our u0 is our initial velocity again, x0 is initial displacement. All of that is then divided by omega sub d, and then multiplied by the sine of omega dt. And if you're curious, you can go through and verify this. So I just want to now go ahead and actually plot an example of what this would tend to look like. Just draw a vertical axis. This will be on the vertical axis, we'll have x of t, and then on a horizontal axis, we're going to plot time. So we're going to start off with that e to the minus beta term, and that gives us some kind of amplitude. That's going to start high and then gradually approach 0. We can call this, well, let's say this is e to the minus beta t. This is what we can call the slow amplitude. So you won't really see this terminology in the study of linear systems like what we're looking at right now, but this does pop up frequently in nonlinear systems. In fact, it's a fundamental property when it comes to studying nonlinear vibrations. We talk about slow oscillations and slow amplitudes. But what the displacement signal actually looks like, and we're going to assume 0 initial displacement in this, it's going to start from 0, it's going to rise up, it's going to hit that amplitude, come down, hit there, and you can see that it's going to oscillate until it damps down to 0. This is our actual x of t. What we would also say is that there's a fast oscillation, so this blue curve represents that fast oscillation, and then the amplitude is a slowly changing amplitude. You won't need to know that in this class, but when we look at these, this is the type of displacement we're going to find. Okay, we're now going to look at an example. We are given that a damped oscillator is released from equilibrium with a velocity of 0.05 meters per second. The oscillator has a stiffness of 250 newtons per meter, a mass of 0.5 kilograms, and a damping coefficient of 4 newton seconds per meter. We're then asked to find the peak displacement that the oscillator achieves, and the time required for the displacement amplitude to settle below 5% of that maximum displacement, or what we could call as the 5% settling time. Okay, so let's get started on this. So, first of all, since the oscillator is released from equilibrium, we know that the initial displacement must be equal to 0. And we also know that the initial velocity, or x dot of 0 or u sub 0, we know that these must be equal to 0.05 meters per second. And if we really wanted to, we can include the units for the initial displacement, which is of meters. If we scroll back up here and take a look at our displacement, since the velocity, since the initial displacement actually is 0, we will not have this cosine term, and then we won't have this second term that multiplies sine. And as a result, the displacement is simply going to be x of t is equal to u0 divided by omega d times the sine of, and actually I left out the exponential, so e to the minus beta t times the sine of omega dt. So that's our displacement. Now, to find the maximum displacement, we're going to need to find the time where the velocity is equal to 0. So to find the maximum displacement, we can say need to find, let's say t star for the case where x dot of t star is equal to 0. So we need to find that time where the velocity is 0. From here, let's go ahead and compute the velocity. We're going to take a time derivative of the displacement to do so. We're going to need to do product rule here. So we're going to have u0 omega d. In fact, when we take a derivative of the exponential, we're going to get minus beta times u0 divided by omega d times e to the minus beta t times the sine of omega d t plus, and now we need to take a derivative of the sine part, so we're going to end up bringing out an omega d and canceling that. So we have u0 times e to the minus beta t times the sine, oops, that should actually be the cosine of omega sub dt. That's our velocity. Let's clean this up a little bit. And for one, we can pull out a u0 and an e to the minus beta t. So x dot of t will be equal to u0 times e to the minus beta t. All of that multiplied by cosine of omega dt minus beta divided by omega d times the sine of omega dt. Okay, so now that we've computed the velocity, we now want to find t star. So x dot of t star, this must be equal to 0. That's our condition. In order to find the maximum displacement, we must have a 0 velocity. This is then equal to u0 e to the minus beta t star times the quantity, the cosine of omega dt star minus beta beta divided by omega d times the sine of omega d t star. Okay, so everything outside of the square brackets, the u0 times the e to the minus beta t star, that can only be 0 for infinite time, which means that everything inside the square bracket must instead be equal to 0. So we get here that the cosine of omega d t star minus beta divided by omega d times the sine of omega d t star, that must be equal to 0. From here, what we're going to do is we're going to move the sine term, we're going to pull that on over to the other side. So we'll get that the cosine of omega d t, this is equal to beta divided by omega d times the sine of omega d t star. I left out a star here. Let me go back and add that in here. So we have omega d times t star in the cosine. What I want to do now is I'm going to divide both sides by cosine, and then I'm going to convert the sine divided by cosine into a tangent. So we're going to get that beta divided by omega d times the tangent now of omega d t star, that is equal to 1. We're going to now bring over the omega d and the beta over. In fact, actually, let's just do that right here and save some space. So we're going to multiply by omega d and divide by beta. And then what we're going to do now is we're going to take an inverse tangent on both sides, and we'll get that omega d t star is equal to the inverse or arctangent of omega d divided by beta, such that then t star is equal to 1 divided by omega d times the arctangent of omega d divided by beta. So at this point, we now need to find what beta is and what omega d are. So we need to find beta and omega d. So beta is equal to b divided by 2m, which is going to be equal to 4 divided by 2 times 0.5. So in the denominator, they're going to cancel, and we're just going to get back 4. The units are 1 over seconds. So our beta value is equal to 4, 1 over a second. Now, omega d is equal to the square root of omega 0 squared minus beta squared. And so now we need to find the natural frequency omega 0. Omega 0 squared is going to be simply equal to k over m, which will be 250 newtons per meter divided by kilograms, 0.5 kilograms. This ends up being radians squared per second squared, and it's equal to 500 radians squared per second squared. So omega 0 squared is 500 radians squared per second squared. So then omega d is going to be equal to the square root of 500 minus 16. Beta is 4, so 4 squared is 16. This will then be in radians per second, which is equal to the square root of 484, and that's equal to 22 radians per second. So omega d is equal to 22 radians per second. Okay. So now we're good to, we can plug this back into t star. We're going to find that t star here is equal to 1 divided by 22. Let me rewrite that 1 times the arctangent of 22 divided by 4. And we'll go ahead and compute this. And then this results in a time of 0.0632 seconds. So T star is equal to 0.0632 seconds. And now we need to find that peak displacement, which means we need to then plug in this value into X. So X of T star is going to be equal to U0 divided by omega D e to the minus beta T star times the sine of omega D T star, which is now equal to 0.05 divided by 22 e to the minus 4 times 0.0632 times the sine of 22 times 0.0632. And this then is now equal to 0.0017, and we're going to round here to 4 meters, such that our peak displacement is, in fact, the peak displacement, we're going to call this x sub m, because we're going to use it in the next part. X sub m is equal to 0.00174 meters. And that is the answer to part A. Okay, with that, we're now able to move on to part 2, which is to find the 5% settling time, or the time where the displacement amplitude drops below 5% of the peak displacement. So we want to find some variable T5 where, say that the absolute value of x at t must be less than or equal to 0.05 times xm for all t that are greater than or equal to t sub 5. That's the problem we're trying to solve. So let's go back and rewrite what our displacement was. So we had x at t is equal to u0 divided by omega d times e to the minus beta t times the sine of omega dt. So in this, the only term that will ever have a negative value is that sine term. And every other term is always going to be positive. And in fact, it represents the amplitude. So the part that I've just drew the squiggle line under, that is our amplitude. Let's call it A of t. So this sentence up top translates into finding times where A is either less than or equal to 0.05 times that peak displacement xm. What that then means is that we need to find u0 divided by omega d times e to the minus beta, and we'll put a T5 in here. This must be less than or equal to 0.05 xm. And that's what we're going to now solve for. So what we're going to do, in fact, we'll just rewrite that expression down here. We're going to bring over the u0 and the omega d onto the other side. So we will get that e to the minus beta T5 must be less than or equal to 0.05 times omega d times xm divided by u0. We're then going to take a natural log of both sides to get rid of that exponential. And so we'll have minus beta times T5. That's from taking the natural log of the left-hand side, which is then equal to, or it needs to be less than or equal to, the natural log of 0.05 times omega d times xm divided by u0. And now we can solve for T5 by dividing by minus beta. In this case, T5 must be greater than or equal to 1 over beta times the natural log, the natural log of 0.05 times omega d times xm divided by u0, which is now equal to 1 over 4 times the natural log of 0.05 times 22 times 0.00174. All of that divided by 0.05. Conveniently, the 0.5s cancel out, making it so that it's just easier for us to plug in the numbers. And from there, we find that the 5%, and I'm just going to write this out, 5% settling time, then I'm going to plug in the numbers. That time is going to be, I'll call it t sub 5%, is equal to 0.8162 seconds. And that is the answer here to part B.